Welcome everybody to my thesis presentation regarding the survivor selection in the plant propagation algorithm. And I directly start this presentation by introducing what is the plant propagation algorithm. It is an evolutionary optimization algorithm belonging to the class of Metaheuristics, which means that it includes some randomness. So every run you perform with the algorithm is rarely the same. Furthermore, it's a crossoverless algorithm in contrast to many genetic algorithms, which include crossover and mutation to generate offspring. The plant propagation algorithm creates offspring only by employing mutation. And the key idea of the plant propagation algorithm is that better performing individuals generate more offspring with less mutation, where worse performing individuals generate fewer offspring with more mutation. So now I will elaborate a bit more on the process of the plant propagation algorithm. There is a population of individuals. We will call this the parent population, which is either from previous generations or from initialization, which creates offspring. These offspring are mutated parents. And as I mentioned, the mutation depends on the fitness of the individuals. And for the plant propagation algorithm, every parent creates offspring, meaning that there is no parent selection method in the plant propagation algorithm. The next step in the process is combining both parent and offspring and selecting the best individuals to participate in the next generation. This last phase, selecting the best individuals, is part of my research, which I will elaborate on next. First, parameter research is very important because it determines the way an algorithm performs. It can greatly influence it. For the plant propagation algorithm, previous research is performed on the maximum offspring size, population size, and the fitness function steepness, performed by de Jonge and van den Berg and Vrielink and van den Berg. An unresearched parameter for the plant propagation algorithm is the survivor selection method, the topic of my thesis. It is a discrete parameter, meaning that according to Professor Eiben from the UvA, that it's the only method of testing this parameter is sampling. It can be stochastic and non-stochastic, and it, as I found, it influences exploration and exploitation. This brings me to the research question, which is, to what extent does the survivor selection method influence the performance of the plant propagation algorithm? Where, as I will mention later again, the performance is defined as the error with respect to the global optimum of a function. So continuing with my research, what did I do? I implemented 14 benchmark functions previously used in literature, of which 5 are two-dimensional and 9 are n-dimensional, with dimensions 2, 5, 10, 20, 50, and 100. So that makes a total of 59 benchmark function instances. The following slide, I will present some benchmark functions in 2 dimensions as an example. Here we see the cigar, the sphere, the rastrigin, Schwevel, Eckley, and Asem. And we see that these have very different properties. For example, the cigar and sphere have a flat surface going towards the global optimum. The rastrigin and Schwevel contain many global optima for an algorithm to get stuck in. And the Eckley and Asem functions present a plateau-like structure that provide very little information on algorithms on where to traverse to. So what did I do to test this parameter? I implemented 8 different selection methods, among which the default selection method of the plant propagation algorithm. Next, I ran all 8 selection methods with the plant propagation algorithm 15 times on all 59 benchmark function instances. And one run took 10,000 function evaluations. So after 10,000 function evaluations of the objective function, the run stops. This resulted in a total of 7,080 experiments, of which I took the median run per selection method to exclude outliers because the plant propagation algorithm contains stochastic elements. So if you don't include multiple runs, for example, if you include only one, that could be that that specific run got lucky with initialization or other forms of stochastic parts. So to increase reliability, I performed it 15 times and selected only the run with the median performance to analyze further and compare. The selection methods I implemented, I will discuss these quite unelaborate, and I will stand still at tournament selection a bit longer, which I will explain in a minute. But first we start with the default selection method of the plant propagation algorithm, plus selection. The plus selection, as seen in the animation before, selects both the offspring and the parents. In one group, selects the best individuals to participate in the next generation. Then we have the comma selection, which does not consider both parents and offspring, but only the offspring. Then we have roulette wheel selection and elitist roulette wheel selection, which work both with the same, at the same way. The roulette wheel selection assigns a selection probability to each individual. And important to notice is that individuals are candidate solutions in the search space. So when I talk about individuals, those are solutions in a search space. So roulette wheel selection assigns a selection probability to each individual according or proportionate to their fitness. So very fit individuals have a very high selection probability and very unfit individuals very low. The elitist roulette wheel selection method works approximately the same. It does the same, except it selects one less individual, keeping a spot open in the new population for the best individual of the parent and offspring populations. So that's why it makes it elitist. Next, we have linear ranking. As I mentioned, the roulette wheel selection assigns selection probability proportionate to the fitness. Linear ranking does so by assigning selection probability according to rank. So you combine the parent and offspring population, sort them by rank, and assign selection probability according to their rank. So this means that if a very fit individual will not dominate the whole selection procedure because it's that much fitter than the worst performing individuals. And next we have the tournament selection, which I will elaborate on a bit more. It is a bit much, but here again we see the animation of the plant propagation algorithm. But now at the bottom we see that there are tournaments included. So we select individuals from the parent and offsprings, randomly place them in tournaments. From the tournaments, the best individual is passed through to the next population. So an individual can end up in multiple tournaments, and therefore individuals can end up as duplicates in the, duplicates can exist in a new population. So an individual might be selected multiple times for a new population. So then I included, for the tournament selection, I included 3 variants. The tournament selection -R standing for without replacement. So this means you select an individual, you do not place it back directly in the selection pool, so in the parents and offspring, but first fill this tournament and then place them back. This means that they cannot be selected for the same tournament multiple times. They can still be selected for multiple tournaments. Tournament selection with replacement means that they can be selected multiple times for the same tournament. And elitist tournament selection, which is tournament selection with replacement, except one spot is left open for the best individual from the parents and offspring population. As a last remark, the selection procedures or selection methods actually that are stochastic, so they work with the selection probability. There, for all these methods, duplicates can exist. So all roulette wheel variants and tournament selection variants can include duplicates in the final population, which appear to be important, as you will see in several slides. So after performing all these experiments, I gathered the results and compared what the best the best selection method was, presented in this graph. We see on the vertical axis all tournament selections, selection methods abbreviated, starting with elitist tournament selection without replacement, tournament selection with replacement, comma selection, plus selection, linear ranking selection, roulette wheel, and elitist roulette wheel selection. What this plot shows is the number of times the selection method outperformed all other selection methods. So when it had the lowest error on a benchmark function instance of all 59 benchmark function instances. As you can see, the elitist tournament selection outperformed all other selection methods on 56% of all benchmark function instances, which I believe is high. Next, we have two tournament selection methods, 12 and 14% outperforming. And then there are comma selection and plus selection outperforming 10% and 7% of the benchmark functions, respectively. Then there are at the bottom the roulette wheel selection variants, linear ranking selection, roulette wheel selection, and elitist roulette wheel selection, apparently not outperforming, or rarely outperforming any other selection method. If we look at the tournament selection methods as a group, we see that they outperform all other selection methods approximately 80% of the time. So from this, we can say that for the benchmark function instances implemented in this thesis, the tournament selection ones perform best, and elite tournament selection is the best. And the keen eye might notice that this does not add up to 80 because of rounding. Then diving a bit deeper into the comparison of various errors, because we don't know by how much it outperforms, we look at the following plot. What we see here are various heat maps over the dimensions from 2 dimensions to 100 from left to right. On the vertical axis, we find the n-dimensional benchmark functions only. The 2-dimensional benchmark functions are included in my thesis. And we see the selection methods at the bottom again. Note, however, that that the colors are implemented in a log scale, so the differences can be quite big, while the color changes is subtle. What we see are various patterns. First of all, we see that the error increases as the dimensions increase as well. We also see that there's a group of selection methods that has nearly always a tint darker. Is always a tint darker than the neighboring selection methods, which are the tournament selection ones. It's less visible at the end, but there's still a clear pattern visible. This is in line with the results from the previous graph, that the tournament selection methods outperform, but we do not see, we do see some significant differences, but the differences diminishes as the dimensions increase as well. And then finally, we find two inconsistencies, namely the tournament selection without replacement on the Rastriging and more significantly on the Schwevel function. Why does the tournament selection without replacement perform out of order in comparison to the elitist tournament selection and the tournament selection with replacement? This I hope to answer in a few slides. But first, I go with you to the behavioral analysis. First, recall that tournament and roulette wheel selection methods can include duplicates, and that the parents of the planned propagation algorithm, or included in the planned propagation algorithm, with a higher fitness generate more offspring with less mutation. So first, the behavior I defined as the median fitness, at least that's what we will look at first, on the Rosenberg 20-dimensional or the 20-dimensional Rosenberg function as an example. And I selected the elitist tournament selection plus selection and elitist roulette wheel selection methods as an example, because they all represent a different mechanism, namely tournament selection, a non-stochastic method, and roulette wheel selection method of working. Deterministic, excuse me, that was the word I was looking for. The plus selection is deterministic. So the first pattern we see is that the plus selection has a generally lower fitness, behaving volatile in the lower half of the graph. And recall that the plan propagation algorithm normalizes the fitness values between 0 and 1. So in the lower half of the graph, we find the plus selection. Then we find in the upper half of the graph the elitist roulette wheel selection, but also the elitist tournament selection. The elitist tournament selection has on average a median fitness of 76% of the time it has a higher median fitness of 0.8. And the elitist roulette wheel selection can be found in the top as well. That's one. The second one I would like to show you is the number of distinct individuals for the elitist tournament selection, plus selection, and elitist roulette wheel selection, again on the Rosenbrock function in 20 dimensions. What we find here is the number of distinct individuals, which are related to the number of duplicates, which cannot happen for the plus selection because it always selects the best. There are no duplicates included, so therefore it has a constant number of distinct individuals. Then we have elitist roulette wheel selection and elitist tournament selection, which can include duplicates and do so. However, the elitist roulette wheel selection does less so than the elitist tournament selection. The elitist tournament selection quickly deteriorates in diversity, deteriorates, excuse me, in diversity. On average, it has only 10 distinct individuals. So to summarize, elitist roulette wheel selection has a higher fitness with a higher diversity, plus selection a lower fitness with a higher diversity, and the elitist tournament selection a higher fitness with lower diversity. What does this mean? More exploitation. Because if individuals, which are duplicates at the same point in a search space, create offspring with few mutation, the area around that individual or close to that individual is more extensively searched than those of than for example the plus selection method. So it exploits more. This is very interesting when considering the outliers in the heat map. Because what did we find? The Rastigen and Swavel function for the tournament selection without replacement performed out of order. Taking these two benchmark functions in 2 dimensions, we find that they contain many local optima. One downside of exploiting too much or too much exploitation is the disability to escape local optima. Why the tournament selection with replacement and elitist tournament selection elitist tournament selection did not get stuck in local optima, I don't know, and it's a strong suspicion that this happened. However, I could not find any evidence why the elitist tournament selection and tournament selection with replacement did not get stuck. To conclude my presentation, I will summarize the findings. First and foremost, the tournament selection methods as a group outperform all other selection methods. Most of the time, namely between around 80% of the time. With the most outstanding method being the elitist tournament selection, outperforming all other selection methods 56% of the time. And I found that for these benchmark functions in my research, the tournament selection employs more exploitation and therefore could outperform the other selection methods. Future research should investigate the consequences, because in general, too much exploitation is not necessarily a good property. However, for these benchmark functions, it appeared to be beneficial. With this, I conclude my presentation. Thank you for listening, and all questions are welcome.
Thank you, Nilius. Yeah. Thank thank you very much for your great presentation.
Thank you.
Yeah, so now I think, Professor, do you have any questions for Niels?
Not at the moment. I'll come maybe later.
Okay. Okay, done.
Thank you.
So that's an easy escape for you today, Niels, obviously. But Abdel is known to come back like a boomerang, so hold on to your shorts. Just cut me off, Christian, if I'm going to be too long. Which shall we do first? Let me just ask 3 questions. Would you like to start with a question about the results or about the prior work in the thesis?
Prior work.
Prior work?
Yeah.
Okay. So I was looking in the thesis. I was reading about. You also told us a little bit about it, about the parent selection method.
Yeah.
Right. And I'm going to make it tough for you. I'm going to read it out of the thesis. So you say for that or maybe I misunderstood, but it's also possible. Very small chance. That for genetic algorithms, that the population of individuals resulting from the parent selection step is called the parent population, and that's where I got a little bit confused. So can you explain to me, like for PPA on the one hand, and for generic genetic algorithms on the other hand, what the concept of a parent population and parent selection exactly means?
So the parent selection refers to the process of selecting what individuals will reproduce, either via mutation or crossover. The individuals that reproduce are combined, but they're placed separately to reproduce. But which is the parent population, because the plant propagation algorithm does not select these parents, you could also say it selects all parents. So in final, they are all placed in the same population, the population that generates new offspring, the parent population. So those individuals that will reproduce are present in the parent population.
Yes. So I understand. So the whole idea is that you have some population of individuals.
Yeah.
From there, you create the parent population by the parent selection method in GAs, in normal GAs.
Yeah.
And from there, you make the children.
Yeah, because for normal GAs, it's not necessarily true that genetic algorithms, it's not necessarily true that all individuals generate offspring.
Yes. This is true. Can you go to the heat maps, please? To the bluish heat maps.
Let me see if I can do that quickly, and I can.
Yes. So what was my question? Oh yeah, I remember. Okay. So you want an easy question or a hard question?
The hardest.
Yes, of course. I only have a hard question. It was a trick question. I don't have an easy question. It's just a hard question I have. So what I see here is very interesting. You pointed out this vertical band, which you see, maybe with some imagination, maybe without some imagination. I'm not really sure, but I see it too, so it must be there. Around ETS, TSR, and TS plus R.
You mean these?
Right. Yes. Thank you for pointing that out. Very, very, very good. Yes, that band, and you can see those kind of patterns and some other patterns reoccurring as the dimensionality increases from 2 to 5, 10, 20, 50, and 100.
Yeah.
And now I was wondering, because you were talking about the work of Marleen de Jonge. And Marleen de Jonge she used the same benchmark, which is very smart of you to choose actually the same benchmark functions, because that allows us to get really deep into these kind of questions. And what she found is that the stability of the performance, how did you call it? Maybe she called it a robust, the sensitivity of the parameters for PPA, it dropped for some functions as the dimensionality increased. So we use the same function, we use the same method, we use the same parameters, and what happens as the dimensionality increases, the sensitivity drops. And for some others, the sensitivity goes linearly, approximately linearly up. And for even others, there's an up-down phase transition in sensitivity. And I was wondering, do you see any kind of pattern? So if I look at the cigar horizontally across the dimensions, I see some pattern occurring. And if I look at the Ackley horizontally, then I also see some pattern occurring. Can you say anything about that?
Well, what I can say, I hope the pattern you are referring to is that these are continuously a bit lighter than these. Mm-hmm. So we continuously see that from the comma selection to the elite red wheel selection, they are a bit lighter than these. Mm-hmm. And this happens over all the dimensions. Mm-hmm. But for the Ackley, it seems to not decrease in error. Mm-hmm. Or sorry, increase in error, decrease in performance. Mm-hmm.
Yes, yeah, this is almost what I mean. So for the cigar function, the tournament selections outperform all other methods, but do they outperform more or do they outperform worse on higher dimensionalities?
That I don't know. As you can see, the difference diminishes, so at least the colors become less separable. So therefore, yeah, it seems, I can't say for certain, it seems that the difference diminishes as well.
Yes, I agree. And actually the difference does not appear at all in 5, 10, exactly, 20,
which is also the case for, in later stages, a bit for the rastrigin and the Schwevel function.
And now the really interesting thing is that Wouter finds the same when it comes to pure performance. Marleen finds the same when it comes to parameter sensitivity. And therefore, there must be something inside that function that controls the behavior of this algorithm.
Yeah, which could very well be the, let me take the high modality, multimodality. So if they perform all very bad, you see little difference because they all perform very bad. And if one does not, approach the global optimum, no, I see some.
No, actually it's also multimodal, so that cannot be it. Okay, I will stop now with my question. I have one more if time allows it, but let's go to Abdel and Christian first. And Christian, back to you.
Yeah. So I was wondering, can you show me again, Nilis, the slides where you show the functions and the percentage of how the ones outperforms. Yeah, that one.
Yes.
Yeah. So what I see in this plot that for example the tournament they all cover all the dimensions, up to 100.
Yeah.
Yeah. But for example, if I have to look at low dimensions, let's say 2 or the one that, for example, the 5 dimensions, with replacement and without replacement, it almost performed the same. But for example, for the 20 dimensions, it doesn't work.
Yeah.
For why do you think? It's my opinion I think I misunderstood something. Why?
No. It's perfect. It's a very good question. Thank you, Christian. And for this, I will go to the heat map again, where, as you can see, the differences between the tournament selection methods are very slim. There's, for example, on the 2 dimensions, but also on the, I think you mentioned 10 or 20, didn't you? 20 or 5. So the differences here are very slim, but in all dimensions. So if the tournament selection, for example, elitist tournament selection is just slightly better, maybe by chance, maybe by exploiting a bit more because it has an elitist version, because it always contains the best or includes the best individual from previous population. There's just an edge over the other tournament selection methods, but it's, yeah, as you can see here, really, really slim. So therefore, I think it, yeah, there's no real large reason behind it why the elitist tournament selection outperformed the other tournament selection methods, and which I didn't include here, but I've experimented with several times, is that the tournament selection methods, and I will give you a sneak peek if it's here. These are the results of the tournament selection methods with respect to the plus selection method only. And here we see that they all outperform the plus selection method. So it's the same type of graph, only now comparing to the plus selection method and not all selection methods. And here we see that they all outperform the plus selection method on, I believe, 8 out of 9 100 dimensional, 8 out of 9 50 dimensional. And here the differences are really, really slim.
Yeah, yeah. Now I say it. The second thing that I found it interesting in your paper, yeah, and I think we already discussed this in our meetings that we had, yeah, and when you were practicing your defense,
yeah.
yeah. So the plot that you showed for the Rosenbrock function in 20D.
Yeah.
Yeah. If you can show that.
Do you mean from my thesis or from my presentation?
From your presentation.
Oh, presentation. Excuse me. Yeah.
Yeah, at some point there is like an elbow rule with the tournaments with E, yeah, between 50.
And do you mean the top plot or the bottom plot?
The bottom one. The bottom
one.
Yeah.
You mean that they deteriorate?
Yeah. So you mentioned that some characteristics of this the selection of the tournament.
Yeah, sorry.
Yeah, I would like to know why it doesn't drop.
Drop
like,
to low.
Yeah.
Why not go to 0, for example?
Yeah, for example. Yeah.
Yeah. Okay, very good question. One of the aspects of the plan propagation algorithm is that if all individuals with the same what do you call it? If all have the same objective value, they are assigned an equal fitness value of 0.5. So that means if we include, if they all have the same fitness value, they all have the same selection probability because they are 0 distinct individuals. So if I say this correctly, this means that it will not likely go to the 1 because 0 is not possible, because then it will select all individuals equally, or it will pick all individuals with an equal selection probability.
Okay.
And why it doesn't approach, for example, 2? For me that's hard to say. I don't have an answer to that one.
Thank you for your answer, Nilis. Professor, do you have any questions?
No, I'll come in a little bit. Not a question really, just a remark. And can you go back to Nilis, please? Thank you, by the way, for a very, very good presentation and the reports. If you go back to the heat maps again, I just have a remark to make. So this heat map, for instance, or maps, it would be nice to, if you were to rearrange them, for instance, with, if you look, for instance, at Schwefel and tablets, if you moved them up just below ellipse, for instance, then you would see, if you like, patterns a little bit better. Now then, the interesting bit here, you look at Ackley, it seems as if if you go all the way for all dimensions, we have got similarity of performance of all selections, and that shouldn't be strange, because Ackley is designed to be a nightmare for search, isn't it? Now then, and then you go, as you go up, that one, of course, but the others too, as you go in dimension, then you will see that behavior is about the same. Why is that? Because my feeling is that when you are in low dimensions, you can basically complexity, if you like, difficulty of problems appear more kind of more heightened, more emphasized when you in small dimensions. So for instance, a problem which is easy, when in low dimensions it is easier. You know what I mean?
Yeah, I understand. Yeah.
So if it's easy in low dimensions, it's even easier. But as you go in high dimensions, even an easy problem suddenly becomes difficult in high, and therefore as you go in dimensions, so these problems which in low dimensions seem to be quite different, and we see the performances of these selections actually kind of are clear. They are quite, you see the differences as you go in dimensions. They just become basically, they really behave in the same way, and it does make sense, doesn't it? It's really
because it becomes too hard, but harder. That's I think the
exactly. So it all comes down with the definition of hardness. If you like a hardness, if you like, there is a point at which then all the problems really, they're all nasty, they are all hard, high dimensions, and therefore you expect behavior to be the same for any tournament selection or almost any algorithms really. If you go higher and higher, you will not find much difference between even heuristics or metaheuristics. So that's the point I want to make. The other, if I'm allowed to add another one, is your point on local exploitation, okay?
Yeah.
So if you like, if you say, oh, there is what is global or exploration versus exploitation, this thing only makes a difference or makes sense if you know how far are local optima, because you may think that you are exploiting, so you have a local optimum, and then you feel like you change it. If you like in the neighbor, you choose in the neighborhood, and you think you are exploiting. In fact, you have no idea how these local optima are distributed. It may well be that just a little change will take you to the global optimum, and therefore, while you think that you are exploiting, actually you are not going down to the bottom of the local optimum. You are actually changing. You are moving away from it to something else, and which means you are in fact exploring. You know what I mean? So there is a kind of a very fine, well, basically, when you think about it hard enough, you will realize that talking about exploitation and exploration is very, very rough. It's not, it's really, you have to understand your landscape, the search landscape very well. If you knew it very well, you could see, then you could say here I'm exploiting and here I'm exploring. if you don't have it, which we don't, if someone throws at you a function that you have not seen before, or even if you have seen it before, but as you go in higher dimensions, you have no idea what it looks like, what it looks like, you really cannot tell.
No.
So it's kind of, when you say it's good to explore that thing, it is, but it's a very, very hard task. It's kind of,
Yeah, I agree. I think I should have rephrased it to with the aim of exploiting, instead of, because I can't say if it actually exploited more or maybe moved away from the global optimum, goes over a peak, for example, and then is in a very different place.
yeah, absolutely, absolutely.
So it's, yeah, regarding the aim of exploitation and exploration.
I am done here. That's it. Thank you.
Thank you, Professor. Yeah. Dan, I think you can have the potentially one more question, and we're gonna stop the QA.
Okay, awesome. Thank you. Can you go to the behavior analysis again, Niels? Because I'm still, and maybe I just cannot get my brain around this yet. But so the median fitness, is it like the median error, or does high fitness mean very low error? Top diagram.
Yeah, I understand. Because my task is to minimize
Yes.
the fitness, the fitter an individual,
Yes.
the lower the objective value.
So it says here that elitist roulette wheel selection is very close to the minimum in the median case over generations.
Well, because it is normalized, if you have all very bad, individuals, the average, or the, excuse me, the normalization will cause at least some to be very high. So if they are very densely packed together at a very bad spot, the median fitness is high.
But the median fitness is actually the median fitness of the population.
Of the population. So this means that at least half is above 0.9. If I say this correctly, yeah.
So that means that. So what does that mean? I cannot get my brain around.
Yeah. Okay.
What is the difference between plus selection here and elitist roulette wheel selection in terms of median fitness on the top diagram?
Well, it's in the difference between plus selection and elitist. Sorry, which one? Roulette wheel or tournament?
No, the best and the worst. The elitist roulette wheel and the default.
Right. The difference is that the objective values. Let me think. Yeah, the fitness of the plus selection is most likely, I cannot say for sure, is most likely more spread, has more diversity, which is also present in the bottom plot. Because there is more diversity, there's a larger chance of them being stretched out.
Yes, yes.
So
I thought so, yes.
Yeah, so the elite roulette wheel selection also has a higher diversity, but it is a bit lower. I think, let me see, it's on average 25.9 over the generations. The median average is 25.9. And what you see is that, or what the elitist roulette wheel selection can do is it selects the best individuals, for example, over and over again. So if it selects the best individuals, for example, it fills it 95% of the best individuals. That means they're all really packed together at a very bad spot with one or two minimum objective values that cause the median objective value to be very high.
Yeah. Makes sense. Okay, so I just have a very short final question. Considering all these results, would you say that there are much better alternatives for PPA selection method than the default selection method? And would you say that original authors and inventors of the PPA algorithm have simply made a giant scientific blunder?
No, that I can never say. What? No. I think, and that's what literature says so as well, that in general you want a high diversity. However, here it shows it got a low diversity and perform better.
Yeah.
So actually this goes against literature. So either my research is wow, or there are some other things that the PPA employs. It could be that the plant propagation algorithm, for example, the mutation size, maybe it could be that's the problem, or that problem not even, but it could be that there is some improvements possible there for these benchmark functions.
Yes,
Benchmark function instances.
So yes, I have no more questions, and thank you for the opportunity to tease out a little bit when he came in. I really enjoyed it every time.
Yeah, I think that would be a good idea, Nilis, if this paper can be published in any venue. Yeah, could show interesting results. I think I don't know if you agree, Professor Abda, but
yes, I think you have actually put your finger on very sensitive points, and the point, of course, with all metaheuristics is that they're very difficult to analyze. Now, maybe if you were to do, I mean, I think this paper is publishable as it is. But if you had time, or you are interested to consider other things, is perhaps to look at the idea of randomness, and how I mean, on one hand, I think metaheuristics are all similar. On the other hand, you got to look at them from the point of view of how many arbitrarily chosen parameters or set parameters they involve. My intuition tells me the less the better. Okay, if I have to choose, a one parameter at arbitrarily, it's better than if I have to choose two, and better if I have to choose three. And so if you wanted to compare, for instance, you could say, right, look at GA. For the generic GA has so many parameters to choose, arbitrarily. You have to have a population. You don't know what is the ideal size. You have to choose the rate of mutation, what is the best, the rate of crossover, the length of individuals, and then the tournament, what tournament selection you have to choose, etc. And so there are so many. And then you go back to the other end, post-Harar. I think, I'm biased, I must say, I'm a little bit biased. PPA, the whole point is that you don't have many parameters. And from the beginning, that's what I had in mind. Even the population, technically, you can start with one. You just have one plant, and then you decide how to propagate it. You don't have to start with, say, is it better to start with 10 or 20? You start with one. Yeah. And so you cut down on you think you cut down, but of course you have to decide how big you will keep it, because you cannot just work with one. You start with one, then you will have 2 or 5 or whatever, and then you will have 10, and then you have got 25, but then are you stopping at 100 or are you stopping at 200? So the problem is not gone completely, but it could go for a while. So in your search process, you could do without deciding yet, and then it may well be that could be good, as you said. For potentially, if there is less diversity, it may actually work better. And then therefore you could be lucky if that is true. If what you have just pointed out is true, you could hit in on the optimum straight away, or a good solutions very early on, which is what we want. We want to get good solutions as soon as possible, and that is something worth exploring. So it's a nightmare. You have a kind of underlined very good questions, and there is a lot to do. And your idea that efficiency and low diversity in this case is absolutely fascinating. You have got there a kind of a great question, and that's, I just want to say that it's worth exploring further.
Yeah.
Thank you.
Yeah, agree. Agree. Okay, Nilis, now it's time to put you in the breakout room.